Okay, let's dive right into this explainer. If you're an undergrad sitting through organic chemistry, I'm willing to bet you stared at a textbook page just absolutely packed with confusing acronyms, stuff like AAC1 and BAC2, and thought, how in the world am I supposed to memorize all of this? Well, good news. Today we're tossing out rote memorization. We're going to completely demystify Ingold's 8 mechanistic classifications. We'll look at how they're similar, exactly how they differ, and figure out the actual why behind how these molecules behave.
Here is our roadmap for today's lecture. We'll quickly cover the basics of ester hydrolysis, crack the Ingold code, look at the cold hard proofs of acyl cleavage, compare the acid catalyzed mechanisms, do the same for the base catalyzed mechanisms, and then tie the whole shebang together with a summary.
Section 1. Basics of ester hydrolysis. Let's establish the foundational rules of the reaction itself before we start drowning in that mechanism alphabet soup.
So, fundamentally, ester hydrolysis is exactly what it sounds like. It's splitting an ester right back into its component acid and alcohol. If you've got esterification down, you already know half the story, because hydrolysis is literally the reverse. And, this isn't just some abstract theory on a chalkboard. It has massive real-world applications. For instance, when you apply base-catalyzed hydrolysis to fats and oils, which are basically just esters of long-chain fatty acids, it produces salts. Industrially, we call that saponification. It's literally the chemical basis for how we make soap. But here is a critical distinction you've got to remember. Whether you use an acid or a base totally changes the game. Look at acid catalysis. It's perfectly reversible. It's symmetric. It's entirely driven by equilibrium. But base catalysis? Total different beast. It forcefully drives the reaction forward to completion. Why? Because the acid that forms gets immediately pulled out as a salt. It's an irreversible one-way street. That is an absolutely crucial difference when you're predicting reaction outcomes on an exam.
Moving on to Section 2, cracking the Ingold code. Now that we have the ground rules, how do we actually label these pathways?
Okay, this is where it gets fun. This is your master key. Instead of trying to memorize 8 random strings of letters and numbers, just use this logical legend. The first letter is your catalyst, A for acid, B for base. The middle letters tell you exactly where the bond is breaking. AC for the acyl carbon, Al for the alkyl carbon. And the number at the end, that's the kinetics of the slow step. 1 for unimolecular, 2 for bimolecular. Boom. Once you see the pattern, the code practically reads itself.
And this perfectly illustrates that middle part of the code, the structural difference in the bond breaking. On the left, you've got acyl cleavage, breaking right at the carbonyl group. On the right, alkyl cleavage, breaking at the oxygen-alkyl carbon junction. As a general rule, breaking the bond at the acyl carbon is way easier. But hey, we're chemists, right? We don't just take generalizations at face value.
Which brings us to Section 3, proofs of acyl cleavage. You should always be asking, wait, how do we actually know that? Let's look at the experimental evidence.
The evidence here is honestly airtight. First off, if you run the reaction with heavy oxygen-18 water, that isotopic label shows up exclusively in the acid product, not the alcohol. That definitively proves the OR prime bond stays totally intact. Plus, think about it. If the alkyl bond were breaking, we'd expect to see some chiral inversion or weird structural rearrangements, but we just don't. Esters with chiral R' groups keep their exact configuration, and famously tricky groups, like allylic or neopentyl structures, don't rearrange at all. All of this points squarely to acyl cleavage being the main event.
So, with those rules locked in, how do these 8 potential mechanisms actually stack up against each other when you're standing in the lab? Let's get into the comparative analysis. Section 4. Acid-catalyzed mechanisms compared. Let's group the A mechanisms together and contrast the everyday pathways with the super rare ones. Check out the 2 acid-catalyzed acyl cleavages. AAC2 is your standard bread-and-butter acid mechanism. It goes through a tetrahedral intermediate and kind of surprisingly needs 2 connected water molecules in that intermediate step just to maintain symmetry. Now compare that to AAC1 on the right. Extremely rare. It really only steps in when a massive bulky group, something like mesitoic acid, creates so much steric hindrance that it literally blocks a bimolecular attack. The sheer bulk forces the molecule to drop a leaving group first, creating an acyl carbonium ion in a rare unimolecular pathway.
Now let's look at the acid-catalyzed alkyl cleavages. Al1 is actually somewhat common, but only if the R' group can pop off as a highly stable carbonium ion. Think tertiary or allyl groups. If it can't form a stable carbocation, that alkyl bond simply won't break. Then you have Al2, which is completely theoretical. It has literally never been observed. Why? Because it would require water to act as an SN2 nucleophile against an alkyl carbon, which, under these acidic conditions, is practically impossible.
Section 5. Base-catalyzed mechanisms compared. Let's shift gears to the B mechanisms, where you're going to see one pathway totally dominate the landscape.
When dealing with bases, BAC2 is the undisputed king. This is the classic, everyday saponification mechanism. It proceeds via a tetrahedral intermediate with acyl cleavage. If you see a textbook base hydrolysis problem, it's almost certainly BAC2. On the flip side, BAC1 is a total ghost, never observed. It relies on an SN1 mechanism where an alkoxide group, OR-, has to act as the leaving group. And chemically, an alkoxide is just a terrible leaving group for an SN1 process. It simply won't leave.
Finally, let's compare the base-catalyzed alkyl cleavages, which are wild because they are so rare. BAL1 only pops up in neutral or super weakly basic solutions where the hydroxide attack is incredibly slow, which gives a stable carbonium ion the chance to form instead. And then there's BAL2, an extreme rarity. It requires hydroxide to attack an alkyl carbon when an acyl carbon is sitting right there. You really only see it in specific strain relief scenarios, like opening up beta-lactones. And what's truly mind-blowing about BAL2 is that it's the only mechanism requiring a chiral inversion of R'. Sometimes, it even spits out an ether instead of an alcohol. Crazy, right?
Section 6. Summary of the mechanisms. Okay, let's synthesize all this data so you actually have a functional framework for your exams. Take a look at this master matrix from the source material. It elegantly maps out every single intermediate and slow step we've just talked about across both acid and base environments. Notice how the similarities line up horizontally by cleavage type, while the molecularity dictates the number of steps in the slow phase. It's like a giant puzzle fully assembled. This right here is your ultimate study guide. But let's simplify it even further based on reality.
By grouping these mechanisms by frequency, you can just cut through the noise immediately. You know AAL2 and BAC1 are impossible. They simply don't happen. You know AAC1, BAL1, and BAL2 require highly specific, weird conditions, like extreme steric bulk or intense ring strain. Because of that, you can confidently predict that either AAC2 or BAC2 is going to govern almost any standard ester hydrolysis problem you face, with AAL1 only stepping in if there's a super stable carbocation in acid.
So, I'm going to leave you with a final puzzle to test out your brand new code-breaking skills. If you were handed a highly sterically hindered ester and it was dissolved in concentrated sulfuric acid, which rare mechanism would you predict to dominate? Think about your catalyst, think about where it cleaves, and think about the kinetics forced by all that steric bulk. Stop memorizing, start understanding those slow steps, and best of luck on your organic chemistry journey.